Welcome to all the students in subject of design of transmission system, the sliding and rolling contact bearing. Today we discuss about life of bearing. Firstly we discuss the selection in proper size of bearing is depend on the expected life of the bearing for a given application. If the expected life of bearing is not very high, then the lower series bearing can be selected, but it increases the frequency of bearing replacement. The life of bearing can be expressed. It is used for defining bearing life for application which do not run at a constant speed, that is automotive vehicles. Bearing life in number of hours of service. It is used for defining bearing life for applications which run at a constant speed, that is in industrial machines and electric motors. For low and medium radial loads, ball bearings are used, whereas for heavy loads and large shaft diameters, roller bearings are selected. Self-aligning ball bearings and spherical roller bearings are used in applications where misalignment between the axis of shafts and housing is likely to exist. Thrust ball bearings are used for medium thrust loads, whereas for heavy thrust loads, cylindrical roller thrust bearings are recommended. In deep groove ball bearing, angular contact bearings and special roller bearing are suitable in application whereas the loads acting on the bearing consist of two components, that is radial and thrust. In rigidly controls the selection of bearing in certain applications like machine tool spindles and double row cylindrical roller bearings or taper roller bearings are used under this condition. The line of contact of these bearings as compared with the point of contact in ball bearing improves the rigidity of the system. Noise becomes the criteria of creation of selection in applications like household appliances. Under the circumstances, deep groove ball bearings are recommended. In designation of ball bearings, the bearings are designated by number. In general, the number of consist of at least 3 digits. Additional digits or letters are used to indicate special features, that is deep groove filling notch. The last 3 digits give the series and the bore of the bearing. The last 2 digits from 4 onwards, when multiplied by 5, give the bore diameter in millimeters. The most common ball bearings are available in 4 series as follows. First, extra high 100, second light 200, third medium 300, fourth heavy 400. That is, if a bearing is designated by the number of 305K, it means that the bearing of medium series whose bore is 0.05 into 5, that is 25 mm. K means it is taper to roller bearing. In static load rating or static load carrying capacity is shown by C0. The load carried by a non-rating bearing is called as static load. The permanent deformation which appear in balls or rollers and race weighs under static loads of moderate magnitude increase gradually with increasing load. Therefore, the permissible static load is depend upon the permissible magnitude of permanent deformation. Experience shows that a total permanent deformation of 0.0001 times the ball or roller diameter occurring at the most heavily loaded ball or roller and race contact can be tolerated in most bearing applications without impairment of bearing operation. The basic load rating is defined as the static radial load in case of radial ball or roller bearing, or axial load in case of thrust ball or roller bearings, which corresponds to a total permanent deformation of the ball or roller and race at the most heavily stressed contact equal to 0.001 times to the ball diameter. It is given by Strebuk equation. In Strebuk equation, figures show the forces acting on the race through the rolling elements which supports the static load CO. So forces is like P1, P2, P3, angle is beta, then CO. So CO is equal to P1 plus 2P2 cos beta plus 2P3 cos 2 beta. Also delta 2 is equal to delta 1 cos beta, or delta 2 upon delta 1 is equal to cos beta. So delta is directly proportional to P raised to 2 by 3. Therefore, it is very important derivation. Del 1 is equal to C1 P1 raised to 2 3 and D2 is equal to C1 P2 raised to 2 3. So putting this value, we know that P2 is equal to P1 cos beta raised to 3 by 2, P3 is equal to P1 cos 2 beta raised to 3 by 2. So after this, putting this value, we get the equations. M is equal to, in bracket, 1 plus 2 cos beta raised to 5 by 2 plus 2 cos 2 beta raised to 5 by 2 plus dot dot. If Z is the number of balls, beta is equal to 360 upon Z. The values of M for different values of Z are tabulated as follow. Z is given as 8, 10, 12, 15. M is equal to 1.84, 2.28, 2.75 and 3.47. It is seen from the above table Z by M is practically constant. Strebuk suggested the value for Z by M as a 5, or M is equal to 1 by 5 Z. Substituting this value, CO is equal to 1 by 5 in bracket Z upon P1. From experimental evidence, it is found that the force P1 required to produce a given permanent deformation of the ball is given by P1 is equal to KD square, where D is the ball diameter and the factor K depends upon the radii of curvature at the point of contact and on the moduli of elasticity of material. From equation, CO is equal to K d square Z upon 5. The above equation is known as Strebuk's equation. So, thanks all of you.